up to now we've been discussing scattering theory. We've connected scattering theory to experiments, so we've given an operational interpretation to the S matrix quantity, or let's say we're on the way to giving an operational interpretation to the S matrix quantity. And today's goal is to show you how to connect this S matrix, these Müller operators, to mathematical problems, how to actually calculate them if you know the Hamiltonian for your system. So up to now it's all very well. We've defined these Müller operators, we've defined the S matrix. I've argued that they are indeed isometries and unitaries respectively, but I haven't really shown how to calculate these things. This is all very well if these things are known to be true, but if you cannot calculate them, then it's kind of pointless. So today's objective is to introduce several ways of connecting scattering objects such as Müller operators with Hamiltonians and potentials, which is what governs the dynamics of the system. So the three topics that we'll cover today are the optical theorem, Green's functions, and T operators. So the optical theorem is the first step towards connecting this cross-section quantity with something we can calculate by just observing that there's a simple constraint that unitarity of the S matrix imposes on the scattering cross-section. So because we know that the S matrix is unitary, we know this quadratic equation here in terms of the matrix elements of S. So quadratic equations are not trivial. And so we might wonder, what's the consequence of such a quadratic equation on observable quantities, such as the scattering cross-section? Can this equation have any consequences at all, or is it totally obscured when we translate everything in terms of scattering cross-section and F functions? Okay, well, the answer, of course, is that this does have some consequences for scattering data from scattering experiments, and we can pretty much directly work that out. So the first step is to remember that we've defined the S matrix, via the S matrix, we've defined an operator called the R matrix, or R operator. And this condition here, this unitarity condition here, obviously has some consequence for R, right? That S satisfies a quadratic equation means that R satisfies some kind of quadratic equation. Let's work it out. So the equation that R satisfies is this one. Okay, but we can simplify that a bit. In that, we can cancel off the identity from both sides, and we end up with this final equation here, which relates R and R dagger, the sum of R and R dagger, to the product of R dagger and R. So this doesn't seem like much, but it has some fairly important consequences for this F function, or the T function. And let's work those consequences out. So we've got R dagger, we've got this equation which is just true, right, on the domain of definition. Let's sandwich this equation between two improper momentum eigenstates, P prime and P. So it's presumably true. And then this leads us to the following equation governing matrix elements of R. And here I'm going to stick a completeness relation in here. So we're going to see what consequences this equation has on the matrix elements of R with respect to these improper states P and P prime. So that's P prime dagger p prime prime p, yeah. Okay, that's an equation. And the reason I've done that is this connects very nicely to the f function, which connects very nicely to the differential cross-section. So there's a reason for doing this. Now, R is connected to T, and T is connected to F. And the connection goes as follows. So this P prime RP, remember, we can separate off the conservation of energy part and get left with the amplitude to scatter from P to P prime. And then T, in turn, is related to F. And F is the thing that's related to the cross-section, or the differential cross-section. So let's translate this equation here, I don't know, let's call it star, into a statement constraining F. So it's only a linear equation away from P prime RP to F. Let's put that data in and see what comes out. And what you find, after straight away substituting this line, is this equation here. Right. So I've cancelled off a delta function on left-hand side and right-hand side, and we're left with one extra delta function here. And then we've got this equation which relates this function and essentially its complex conjugate to some quadratic function of f. And, well, it's a little exercise. At this point, I hope it's not so difficult to see how this exercise works. I mean, you've got a function here, f minus essentially its complex conjugate. So this, I hope that's sort of reasonable to imagine that if I write down we look at the process where P goes to P. If P prime equals P, then you can see that this is just F minus its complex conjugate, so that's just the imaginary part of F for the point for process P goes to P. And then over here, well, this delta function gets spent, and you could do a little calculation and I hope confirm that you get the total cross-section out there at P where we've integrated over the solid angle of the differential cross-section. So this is a super useful, this thing here is called the optical theorem, this relationship between the imaginary part of F and the total cross-section. And it's extremely useful in experiments to check if you're doing your experiment well, right? So if your experiment is a good scattering experiment, then the scattering matrix had better be unitary, otherwise something's gone somewhere, right? So it's got to ensure that you're doing a good scattering experiment, you would have to have that S is unitary. And then the unitarity is directly connected to this relationship between the scattering amplitude and the total cross-section. This is both, these two quantities are things you can determine experimentally, and then you can just check empirically, is this relationship observed? And that gives a good check that you're not creating bound states in your experiment. Another way this equation can be useful is that if you know this quantity, then you know this imaginary part of F, so you get more data about F. If you like, this is the first step towards connecting experimental quantities with theoretical quantities. So we want to make predictions in physics. We want to have some model or some proposed model. We want to make a prediction, have a hypothesis we can reject, do an experiment, and then reject that hypothesis. That's how we get forward in physics. But to do that, we need to connect these theoretical quantities, H, V, the Hamiltonian, the potential, to these experimental quantities, the cross-section and the scattering amplitude. And we need a direct way of calculating one from the other, otherwise what's the point, right? And this is the first step towards doing this. This is just the consequence of unitarity. Let's actually get a bit further now. Let's really connect as close as we can. Let's connect as close as we can the Hamiltonian to scattering information, and then we're really getting somewhere. And we're going to do this via a thing called the Green's function or the Green's operator. So I've got to tell you what that is. I assume you've probably met Green's functions, at least in the context of linear partial differential equations, like the heat equation and so on. And probably for the Schrödinger equation, but we're going to go through it again. Let's consider our favorite Hamiltonian in relative coordinates, the free particle Hamiltonian. And this is meant to be the free part of a scattering experiment. This is what models the particles when they're far away from each other. And here is what models the system when they're close by. So during that short epoch of time when the two particles are close, or they're in relative coordinates, the particle is near the origin, this potential is non-trivial and has some effect on the dynamics of the system. So this thing here is solvable. We know how to diagonalize this Hamiltonian. So that part's kind of easy. This part's hard. There's no other way to say it. It's just hard in general. Maybe you have some numerical tricks, I don't know. But for sufficiently complicated V, there's no analytic solution in general. And what we want to do, though, is exploit as much as we can our solution here for the free part and approximate as best we can the contribution from this hard bit, this potential here. And throughout this course, I've been emphasizing perturbation theory and the variational method as ways to solve these kinds of problems. And scattering theory is no exception. We're going to build quantities that allow us to expand the experimental quantities like Miller operators and S matrices in terms of power series of V. So we're going to imagine V is always small. This is the crucial technique that we're going to use. And to help us there, we're going to introduce some things called Green's operators. Now, Green's operators turn up in various ways. I mean, they're kind of amazing things, right, if you think about it. When you solve a linear differential equation and you put a delta function on the right-hand side. So this is an aside. Just to remind you of Green's functions, suppose you have a partial differential operator like the heat operator, dt minus dx squared. Then if you solve this equation with a delta function at some position y on the right-hand side at time 0, then let's call that solution G. I apologize, it's t equals 0. So we solve the heat equation so that at some given instant of time, the heat distribution is a delta function. Then the resulting solution, let's call it G, is a function of x, y, the position of that delta function, and obviously time. And this is the boundary condition here. So we have this solution G, and this solution G has a remarkable property, right? I'm sure you've done this before. If you integrate the solution G against some function f of y, we get some function of x and t. Right? We've only integrated out the spatial position of the delta function. And this phi x and t has the remarkable property that as t tends to 0, the heat distribution of that solution is exactly f. So G is like a general purpose solution to this heat equation for all possible boundary conditions. if you know G, then you actually know how to solve the heat equation for whatever you like as the initial heat distribution. So Green's functions they encode all the solutions of a differential equation for all possible boundary conditions. That's one way of interpreting them. A second way of interpreting them is as a kind of inverse to this differential operator here. So this is the second interpretation. So I'll write this a bit more heuristically. So L times G equals delta. That's roughly speaking what we're doing here. And if you, this is extremely heuristic, that means that G is kind of like delta on L. If you think of L as a matrix, G as a matrix, and delta as the identity operator. So Green's functions are like the inverses of differential operators. That's a second interpretation. And a third interpretation, which is closely related to these two, comes from perturbation theory. So if you do perturbation theory, stationary perturbation theory, then Green's functions appear in the perturbation expansion for energy eigenstates. I'm going to get this wrong. GV or VG? GV, I think. Plus GV, GV. All right. So if you do stationary perturbation theory in quantum mechanics, these Green's functions appear again, right? Except they're G naught. Right? They come from the expansion for an eigenstate in perturbation theory. So there's three places where the Green function arises, and there's deep connections between these three examples that I just gave. They're not really a directly physically observable quantity. When Z here, when I'm about to define this object, you'll see that this is not a Hermitian operator in general. I got it the other way around. Okay. Z minus H naught to the inverse. So this is not directly a physical observable when Z is not real, because then this is not Hermitian, but it's intimately connected to physical observables by this last equation there. And these operators, they're only defined when Z is not an eigenvalue, or Z is not in the spectrum of H and H naught. And today's task is to connect the scattering cross-section to the Hamiltonian, and the way we're going to connect it is via these Green's operators. Now, knowing how to invert an operator is enormously powerful. Usually, if you can invert a matrix, then you know how to diagonalize a matrix. That's not always true, but it's sort of enough true. And knowing how to invert it for all possible values of Z, that's really essentially equivalent to knowing how to diagonalize H. So we don't expect to be able to calculate G of Z for very complicated Hamiltonians. It's just very unlikely, right? Because if we can't diagonalize the Hamiltonian, why on earth would we be able to calculate G? But we can derive a perturbation expansion for G when V is small. This is the most important feature of the green function, or green operator. So that's the next step now, how to get a perturbation expansion for G, which is hard, in terms of G naught, which is easy, and V, which is easy. To do that, we're going to exploit a little identity. But before that, I'll just say a couple of words about these operators. So typically, they're not analytic. So for positive real values of Z, they're not analytic. And the reason is clear. Every time you hit an eigenvalue of H, this thing is not even defined, right? It blows up. And it's worse when the Hamiltonian has continuous spectrum, because there Z is not even allowed to be in intervals of the real axis. So there's some kind of branch cut going on in general. So, for G naught, we see that immediately, because the spectrum of H naught is the positive real axis, Z cannot possibly be allowed to go onto the positive real axis. There's a branch cut that we have to take account of here. So this is where the spectrum of H naught is on the positive real axis. Z's not allowed to go there. Away from there, we're going to observe that G naught of Z behaves in a sometimes very peculiar way. If you allow Z to go to plus minus I0, which means I epsilon, so if you sort of approach this real axis this way, you approach some point on the real axis this way, or approach it this way, you can end up with different values for matrix elements of these operators. And so they're really not particularly analytic and amenable to complex analytic methods. Nonetheless, we can do a lot, and the thing that allows us to get ahead is the following operator identity. Okay. So we pretty much know what G naught is, because we know what P squared over 2m is. We know how to diagonalize that. So we know how to diagonalize G naught. So that's okay. We don't know much about G, but this little equation here is about how G relates to G naught. So this is an operator equation. You can just check it's true while I'm erasing the board. Just imagine multiplying out the right-hand side. You have let's say 7 arithmetic operations that you have to do to confirm that. So it looks innocuous enough as an identity, but boy is it powerful. Okay, let's see what this baby can do. So, actually I lied, right? So let A equal Z minus H. No, I was right. It was G. Yeah. And B equals Z minus H naught. Okay, so now you can see that A inverse is G and B inverse is G naught. And then we're going to get ourselves a pretty impressive equation. Okay, G equals G naught of Z. That's the first part. Plus, and this is where it comes into its own, G naught of Z V G of Z. Huh. That's pretty cool. And actually there's another one where you can just exchange the roles of G and G naught. And there must be a minus sign. No. G, G naught, G, G naught. Okay. Curious. I feel like there should be a minus sign here. B and A, right? Yeah. Yeah. I think there's a minus sign here. So this is just an identity, but this has a name. This is called the Lippmann-Schwinger equation. And this is the building block of perturbative calculations in scattering theory. Because this tells us that G equals G naught plus something presumably small. So the second term, G naught VG, I mean, hopefully that's kind of small. So maybe you can iterate this expression to get some kind of perturbation theory for G. And that's exactly what we do. Okay, if you know some z and it's not in the spectrum of h, then you know g of z if you know the right-hand side. And let's see what we can do. Maybe we can go some way towards calculating this right-hand side. So as I've said a couple of times now, we know g naught of z. That's pretty easy. If you take some improper momentum eigenstate, apply g naught to it, then we know what the answer is straight away. It's z minus p squared on 2m. Minus 1 of p, and I'll write that as this 1 over z minus ep. So it's a number times by p. P is an eigenstate of improper eigenstate of g naught as it is of h. And so if we apply this guy on p, we get something we know plus something we don't know times something small times something that we do know. It's getting close to something we can approximate. To really exploit the smallness of v, we're going to introduce another operator, and this operator is not just because v is small. We're going to introduce this because it's going to connect a bit more directly with things we can measure in experiments. So this next operator, which is almost the same as the Green's operator, is the one that connects more closely to scattering experiments, and we call it the t operator for a reason. So remember, there's this t amplitude, t function that connects directly to the cross section. This t operator will have a lot to do with that, as we'll see. And the t operator is almost the same as the Green's operator. It's a rather peculiar thing to build at this point, but as time goes on, you'll see that this is a natural thing to do. So we have t. T is just some peculiar function of g. G is just z minus h. And v is small, and v times v is small, and so we expect that t is kind of a small thing. Now I'm going to call this equation star star. And now let's try and use this Lippmann-Schwinger equation to relate t to something maybe a bit easier. So you get on the left, so that means g naught of z times t is the thing we want to consider, t times z. On the right we have g naught of z times v plus g naught of z times v times g of z times v. Okay, if we look at that, stare long enough at that expression down there, well, what do we see? We can see that g naught of v times g equals g minus g naught. So we can do something here, g minus g naught. This bit here is g minus g naught according to the Lippmann-Schwinger equation, but that means that that term here cancels with that, leaving us with a gv. Cool. So g naught of t is g times v. This will be useful. And similarly, if you do it from the right-hand side, everything looks more or less symmetric. You get T of G naught equals V of G. Now let's tie together G and T and G naught. So by the Lippmann-Schwinger equation, that's what this is. We know that G is related to G naught according to this. But this thing here, V of G, well, that's over here, yeah? That's the same as T times G naught. Call this star, star, star. And this is how we relate G to T directly. Put a Z in there. So knowing G is pretty much the same as knowing T because we know G naught. And we can invert this relationship to get T in terms of G. And that's how we relate T and G naught. And this expression is also known as the Lippmann-Schwinger equation, but now for T. So far we've just exploited this operator identity over and over again and introduced some quantities. It's this final equation here that we're going to use to build our perturbation series. So what we have here is a linear equation for T involving stuff we know, V and G naught. And such equations, as soon as you see something like this, you should instantly think iteration to solve it. Whenever you have an equation that looks like x equals a plus mx, well, let's call this b even. Whenever you have an equation like that and you want to know x, what's x? Well, you use the fact that you know that x equals a plus bx, and you substitute in for x, right? You iterate this equation over and over again. And then we know what x is, so we get an ba plus b squared, and x equals a plus bx, and so on. And this will build for us a series for x in terms of stuff we know, namely b's and a's. And this is no exception here. This is exactly what's going to happen. We're going to exploit this equation here, which has t, the thing we want, in terms of a and b, to get a series for t alone. Very remarkable trick. We use it all the time. This is the kind of the fancy way to do perturbation theory. And when do we think this works? Well, this series, we want this series for x here, or t, we're going to get for t there. When is it going to converge? Well, it will converge when these things get smaller and smaller and smaller. That's what converging means. And so you want either that a and b, or their products are small, and that higher products get smaller as well. And one way to guarantee that is that v is weak or small. What this precisely means is not so trivial to explain. Because v is an unbounded operator, just because it has a small coefficient does not make it weak, because it's got eigenvalues that are very large, no matter how weak it is. So for this course, I'm just going to say weak, and that's going to mean you test it out, and if it works, then it's weak. But there are quantitative criteria for when v is actually considered weak. One is the notion of relative boundedness, which we won't cover in this course, but it's very useful. So we set t naught equals v, and then we just apply this equation here to get the following series for t. Should look pretty familiar. This thing's called the Born series. So far, so what? I've invented some mathematical operators and I've got a series for them. What's that got to do with scattering? Well, let's find out. So it turns out there's a deep connection between Miller operators and T operators. Let's find it out. Well, and Green's operators. Let's tie it all together now. So the first thing is to recall what a Miller operator does. It takes some in state, which is describing a free trajectory, I'm going to call it phi, to a scattering state, which is asymptotically the same as this in state, but is on a interacting trajectory. And just for notation's sake, we're going to say that a Miller operator takes phi to phi plus. Why have I written psi? Well, yeah, we can write that. So a Miller operator takes a free asymptotic trajectory to an interacting asymptotic trajectory, and similarly for the omega minus. And we had a definition for the Miller operator. It was like evolve infinitely far in the past with your asymptotic, with your interacting Hamiltonian, and then evolve infinitely far back into the future with your free Hamiltonian. That was the definition. And we're going to use that definition now to connect it to the T and G operators. And the way we do that is with a little integral that we derived. All right, why on earth is this true? Let's find out. This is just another way of doing the limit in the definition of the Miller operator, as long as this phi is in the domain of the Miller operator. Let's just see what we're doing. Let's just undo what we've done here. So this thing here, what is it? Well, it's like the derivative with respect to tau of e to the I tau h, e to the minus I tau h naught. That's what the integrand is there. It's a derivative. So it's we're integrating a total derivative. And what do you get when you integrate a total derivative? Well, you get back the thing that you were differentiating. And so this is none other than that object there, right? So that's why this expression here equals that expression there. But this thing here, this is very, very suggestive. So u of t integrated to infinity, and a v and a u naught of t. Now it's not at all obvious, but once you have some practice at these kind of things, whenever you see integrals of propagators, you should start to think green functions, because the integral of an exponential will turn out to give a green function in these settings. That's not obvious. That's something that you have to get some experience with. Before it becomes second nature. So if we know that the Müller operator can be written in terms of green operators or T operators, then we're very close to expressing our experimentally accessible values in terms of theoretical quantities. Now let's note something interesting. If you have an integral of the form integral of some state vector psi tau from 0 to infinity, and that is absolutely convergent, then you're allowed to add in a little bit of a convergence factor and you'll get the same answer. Okay, the proof of this is not so hard to pull off. You just approximate this integral here with a sequence of such integrals like here and just argue that that sequence converges. So sequence where epsilon, I don't know, goes along the dyadic rationals down to 0 would do it, and then you just argue that this integral is basically this integral for longer and longer lengths of time and then bound the error. So this is not a particularly controversial statement. I do leave it as an exercise to convince yourself of it. Or you can look it up in a book. Now, doing this kind of thing is super useful in scattering theory because we've always got this problem that we end up with Green's functions that need to be evaluated on the real axis, which is stupid because they're not defined precisely there. And doing this here allows us to push ourselves slightly off the real axis, as you'll see. Turn that into a parenthetic remark. So let's just, now this is a parenthetic remark. We're going to exploit that in our integral for phi minus. So phi minus is omega minus on phi. And that equals phi plus I times the limit as epsilon tends down to 0 of this integral here. So as written, that's not quite very close to what we want. We're going to put in a completeness relation here. be able to do something. Watch this. Okay, I did two things at once here, so let's just look through it slowly just to check that this is all right. What have we got here? So we've got U0 applied to P. So I'll just put in the side here the stuff that we've got going on. Right? U0 applied to P. It's just this number. I give this number another name. It's E of P. So is this term accounted for over here? E minus EP of T? Yeah. That's there. So that bit's accounted for. And that's where that U0 went. Now, what else is going on? We've got a minus E epsilon of tau, minus I. So that's plus minus epsilon of tau. So that term here is accounted for. And we've got this thing here. What's that? Minus I, in fact, IH of tau. Well, that's just none other than this guy. So all terms are accounted for. But now, I can make good on this promise that integrals of propagators give green functions, Green's operators. If you look at this thing for a moment, and then you look at this integral that we want to do, this tau integral. So what's the integral of an exponential? It brings down the exponent, doesn't it? So the integral e to the minus kx dx. Such a useful identity to know. That's e to the minus kx on minus k, evaluated at 0 and infinity. And what do we get at the end? Well, we get that this thing converges to 0 when x is infinity, and when x is 0, we get 1 over minus k. That's why integrals of propagators give Green's operators. It's just this little identity there. But it takes a bit of practice to sort of see that in these calculations. So let's do the integral over tau. And then you'll see the reason for this epsilon. See, if epsilon wasn't there, this would be bad. This would be really bad. Because if epsilon was 0, that would be EP minus H. But that is precisely where this operator is not defined. So that's why we need that epsilon. Pushes off that. And now, if you look at that expression, that's looking mighty like a Green's operator. Yep.
I don't understand why we need this epsilon, because I think the EPs are the eigenvalues of the free Hamiltonian.
Aha, yes. Okay. So the question is, why do we need the epsilon when the EPs are the eigenvalues of the free Hamiltonian but not the interacting Hamiltonian? Well, the answer is they're also the eigenvalues of the interacting Hamiltonian. Because the interacting Hamiltonian has continuous spectra on the real line, it's just they're in different, they're a bit sort of smooshed around, but they're still, you don't want to be on the real axis. So if the final Hamiltonian, this interacting Hamiltonian here, did not have continuous spectra on the real axis, then there would be no scattering states. So if you remember this argument from a couple of lectures ago, that means the spectrum of H lies on the real axis and is continuous. But that's bad, right? Because even though EP may not correspond to the same eigenvalue, eigenvector, the same eigenvalue there, this number is surely going to hit a part of the spectrum of H, and then that won't be defined. But it's a good question. Oh no, it's a plus. That's it. We've really done it. We've managed to connect the Miller operator, which is this thing up here, to the Green's operator here. Not completely directly, you have to do this integral over P, but you know, it's pretty good. But of course, you're entitled to complain that the Miller operator is not something that's observable. It's almost observable. I mean, the product of two Miller operators is the S operator. Yeah.
Do I see it the right way that the phi minus and the phi plus are exactly the same expression?
What's going on there? Yes. Are the phi minus and the phi plus exactly the same expression? I hope not. That would be weird. Yeah, they are different. Sorry about this. Yep.
One question: when you did the tau integral, I think there's a minus sign wrong.
So the question.
Check the integral on the top right, bottom right corner of the upper blackboard. I think it should be 1 over k and not 1 over minus k.
Ah, right. The observation is that I've done one of these integrals wrong. Yes, I have. So that I hope fixes up that mistake there. Whether this has any consequence for this calculation here, I don't think this is. I think this is correct. Yeah. Right. Good. Thanks. Yeah. Right. Scattering operator. So this is great. You know, we've managed to express the Miller operator in terms of the Green's operator. Can we do the same for the scattering operator? We ought to be able to, because we know both Miller operators. Isn't it just a matter of multiplying these things out? Well, the answer is yes, but you have to do a double integral. So let's... Another question? Yeah.
Why is there then still a minus I?
Why is there a minus I? I guess you're referring to here, yes?
Because there's d to the...
Why is there a minus I? Oh, because the I is outside of the brackets. So it's either plus I inside the bracket here or minus I outside the bracket, because the inverse just applies to this argument here. Okay. Relation to the scattering operator. So the scattering operator takes in to out states, and it does it by these Miller operators, both of which we've now related to Green's operators. So let's go ahead and just mimic the calculation down there and see where we get. It's sort of surprisingly ugly somehow. Okay, that's just the definition of the Miller operators stuck in there. This is the bit I don't particularly like, but it's not wrong. It's just not very beautiful. Okay, the order of these limits is not important. We could have done the limit t prime goes to infinity first, t goes to infinity first, or indeed they both go to infinity at the same time. Okay, same trick as before. Here's the matrix element of S. That's the same as the integral of the derivative. Now we're going to stick in the convergence factor. And then we replace these in and out states with improper momentum eigenstates. Remember, every time we do this and you get worried, just check that afterwards when you integrate against Gaussians or something, you get the right answer. And then we get this expression here, p prime s p is delta 3 p prime minus p. And here we see the appearance of the T operator, not the G operator. This is the final expression for today, and it's the one that connects the S matrix, which is directly related to cross sections, to the T operator, which is directly related to the Hamiltonian and the potential. All of this mirrors exactly the calculations we did for the Miller operator up to this point. And then you notice that this expression here is equivalent to a delta function, setting P, EP equals to EP prime, which is good, right? We don't want that the scattering process violates the conservation of energy. So this replacement here is expected. And we're just left with this expression here that you have to evaluate. So once you know the T operator, you know the S matrix between any in and out momentum states like that. And so that's made good on this promise of connecting these two quantities. In the next lecture, what we're going to do is actually start to calculate the T and the G operators via perturbation theory and also variationally as well. All right. Okay. Thank you very much.